Hello everyone and welcome to TLE Eliminators PCD for Leetcode Weekly 463. Um, this is Vibhaas and today we'll be discussing all the problems from A to D. How was the contest, guys? Solve 2. Frustrating. Yeah, second was easier, I would say. Okay. So I think most people solved 2 and I don't think you should be worried, Starlord. Like this was a contest on slightly the harder side. So no need to be too worried about it. Okay. So we'll get started with the questions starting from A all the way to D. I'm not sure if my A implementation is the most simple way to do it, but we'll discuss all of them. Yeah. Okay. Yeah. So even the first problem is usually easy, right? In late code, this time the first problem started with medium. So yeah, it was a slightly harder contest, you could say. Anyways, happens from time to time. Sometimes maybe once in a month they give a harder contest. Okay. Problem A. In this, you are given two integer arrays, prices and strategy, where price of I is the price of given stock on either day, and strategy of I is the trading action on either day, where -1 means you're buying 1 unit of stock, 0 means you're holding the stock, and 1 indicates that you're selling the stock. Now, you are given an integer k, and you may perform at most one modification to your strategy. And what is the modification allowed? You can select exactly k consecutive elements. So that means you can select exactly a subarray of size k. Then you can set the first k by 2 elements to 0, which means hold, right? Hold the stock. And the last k by 2 elements to 1, which means sell the stock. Okay. The profit is defined as the sum of strategy of I times prices of I across all days. Return the maximum possible profit you can achieve. All right. And first of all, if you think in terms of stocks, you will question that how can you sell a stock before buying a stock? For example, in one of the examples, you're selling a stock before even buying a stock. But then it's given here that there is no constraints on budget or stock ownership. So all the buy and sell operations are feasible. Okay. So all the buy and sell operations are feasible. So basically, we do not need to think of it as stock. Just think of it as numbers. Okay. Just think of it as numbers. Like basically you have prices of I array, and which is some numbers. Okay, prices of I array is some numbers. Let's say p1, p2, p3. Let's say there's 5 days, so we'll have 5 elements and each will be the price of the stock for 5 days. And then we'll have strategy of I, which is going to be an array which has either 1, 0 or -1. So let's say it has 1 here, and then it has -1 here, then let's say it has 0 here. So basically we just have to consider that what is the maximum possible value of p of I times p1 times strategy of 1 plus p2 times strategy of 2 plus p3 times strategy of 3, basically that, right? So that's all we need to consider. And we need to maximize this. Do not think in terms of stocks, otherwise you'll get confused. Why are we selling before buying and things like that? The question is just phrased in that form, but it does not actually mean real stocks, right? Okay. So I hope that part is clear. Okay. So what exactly is the question asking? The question is asking that we can do at most one modification of this form. Okay, so we can do at most one modification of this form. And what is the modification? So basically our price array, let's say we have a price array which is looking like something like this. So let's say the price of the stock is 10 on the first day, then 12 on the second day, 3 on the third day, 5 on this day, and then let's just put some random values in for our example. Okay, so this is the price array, and let's say we have a strategy array which is something like -1 -1 -1 1 1 0 0 1 -1 1. Okay, so let's say this is our strategy array, and let's say our k is let's say 6. Okay, our k is 6. So basically it means we can choose any subarray of size 6. For example, we chose this subarray. Okay, so we will choose this subarray which has 1 2 3 4 5 6 elements. Okay, if we choose this subarray and we apply the operation here, basically these will become holds and these will become buy, right? These will become hold and these will become not buy, these will become sell, right? So that's why basically the multiplication values for the strategy have changed to 0 for these as well as 1 for these. Okay, so that's what's basically happened, and the remaining values have been untouched. Okay, so these remaining values have been untouched. Okay, untouched, and these also have been untouched. So basically the sum over here will not change. This will simply be 10 times minus 1, and this will simply be 9 times 1 plus 12 times minus 1 plus 14, right? And over here this becomes 12 times 0 plus 3 times 0 plus 5 times 0 plus 6 times 1, 7 times 1, 8 times 1. Okay, because these are being treated as 1 1 1, these are being treated as 0 0 0. Okay, so that's all is basically what the question is asking us. So I hope this much is understood to everyone. This much you can understand that this is what is going on. This is untouched as well as this is untouched. Okay, so next what do we need to do? Basically we need to find the answer with doing at most one operation. So when we say at most one operation, at most one operation, when we say this, it can mean one of two things. Okay, it means you did 0 operations, exactly 0 operation, right? Exactly 0 operations, or exactly one operation, right? That's what at most one operation means. So we did one of these two things, and we have to take the best of both the thing, which will give us the maximum profit, right? We have to choose the best of these two choices, which gives us maximum profit. So exactly 0 operations we can simply find out by doing price of I times strategy of I, and we can sum that. So we have that as our answer. So now we need to focus on the case where we do exactly one operation. Okay, now we're going to focus on the case where we do exactly one operation. Fine. Case of exactly one operation. Now because the size of the subarray is already given to us, like for example we have k equals 6, so we know that for sure the size of the subarray is 6. What we can do is we have not many options. So let's say if k equals 6, then this is one of the subarrays, right? This is one of the subarrays with k equal to 6, and then these remaining will be unchanged. Okay, these remaining will be unchanged. So let's call this value base. Okay, let's store the price of I times strategy of I for these values, the base, and we're going to store it in a variable named base. Okay, so the base will currently contain the values 8 times 0 plus 9 times 1 plus 12 times minus 1 plus 14 times 1. Okay, and what about this thing? Let's call this the sliding window. Okay, let's call this a sliding window. So we'll call this slide equals 10 times 0. Why 10 times 0? Because these will be 0 and these will be considered ones, right? So we'll keep it as 10 times 0 plus 12 times 0 plus 3 times 0 plus 5 times 1 plus 6 times 1 plus 7 times 1. Okay, because that's how the problem statement says, that's what the operation does. So this is what happens for the first operation. Okay, this is the first possible operation we can do. Similarly, the second possible operation which we can do is to choose these 6 elements, right? And another possible operation is to choose these 6 elements. Basically we need to choose any 6 elements and do this, and we can do it at least one, at most once. Or the next one is to choose these 6 elements, these 6 elements, right? Or choose these 6 elements, right? So these are the all the options we have. So now the interesting thing is, when we go from the first option to the second option, right? When we go from the first option to the second option, the new value of base will be this, right? The new value of base will be 10 times minus 1, 10 times minus 1 plus the values over here. So 9 times 1 plus 12 times minus 1 plus 14 times 1, right? And basically the value of 8 times 0 was removed. Okay, so the value of 8 times 0 was removed from here, so we need to keep that in mind. And basically, as you can see, the value of base is only changing by this and this. So basically this value is getting removed, right? This value is getting removed from the base, which means the elements which are outside the sliding window, and this value is getting added to the base. And we can change this in O of 1. If we know, if we have a pointer to both of these positions, we can just change this in O of 1. Okay, similarly, the subarray itself which we are choosing is also a sliding window, so this 10 times 0 is getting removed basically, and this 8 times 1 is getting added also. um this 5, which was earlier 5 times 1, it has become now 5 times 0, right? This 5 was earlier 5 times 1, it has now become 5 times 0. Similarly, this 6 is still remaining 6 times 1, 7 is still remaining 7 times 1, and 8 is still remaining. 8 has been added, right? So 8 is added. Also, since 5 times 0 means we are basically excluding the element, right? So since these are being multiplied by zeros, it's basically like these elements are being excluded. So basically the only sliding window we need to consider is just a sliding window of size k by 2, because these will all be zeros. Okay, so these will all be zeros. So basically what in essence which happened was, this value was added, sorry, this value was removed over here, 5 was removed, and 8 was added to the sliding window. Okay, so 5 was removed and 8 was added to the sliding window, and that's the change which happened in the sliding window. In the base, 8 times 0 was removed and 10 times minus 1 was added. And basically what we need to do now is basically run a sliding window, like this, sliding window like this, calculate the maximum, calculate the maximum of base plus sliding window, let's call that slide. Okay, so initially, um so for base what we're going to do is we're going to remove the last element. So ith value of pi minus si gets removed each time we slide, right? Each time we do sliding window step, the ith value of pi times si gets removed, and the value p of I minus k times s of I minus k gets added, right? So this is how the base will slide. And what about the sliding window itself? For the sliding window, the value um the value p of I gets added, right? Because p of I times 1, which is p of I only, so the value p of I gets added, and the value p of I minus um k by 2. So the this element, middle element, like in this case 5 was there earlier in the sliding window and now 5 is removed, so you can see that that is I minus k by 2 element, that value gets removed. And when we run this sliding window, the maximum value which we require is the maximum value of base plus slide. Okay, so this is for the case in which we remove exactly one, if we do exactly one operation, we have to take max of this case, in the case which we do exactly zero operation. Okay, so that's how we solve this question. um any doubts regarding this? 4 pointer, interesting. It's not that easy, but mainly the problem for A, I think, is implementation. The idea is not very hard if you know basic sliding windows. Thanks for the words, Nishant. Rank improved by 350. That's interesting. um by the way, in the contest I could solve only ABC, although I did after the D after the contest. Yeah, I do think the rank improved a bit, which is interesting. Anyways, um yeah, showing the code now. Before that, let's just discuss the time complexity. Since we're just running a sliding window from 0 to n minus 1, basically we're just sliding this. The time complexity will be big O of n, right? So if you have trouble understanding this solution, I think it's pretty straightforward with some knowledge of sliding window. So you should check out maybe TLE level 2-ish, where sliding windows I think are discussed. I think it's in TLE level 2. Yeah. Okay, so code. So initially I just define n as the size of our prices, and here I'm just finding um here initially I'm just finding the values of all prices of I times strategy of I. Okay, so this is just finding the sum of all of them and setting that to the answer. So this is to solve for the exactly zero case. Okay, so this is to solve for the exactly zero operations performed case, which means array is not prices array is not touched, right? So this is the default answer which we have if we do no operations. Now I define a value for slide. So this is my slide, which will hold the value for the sliding window, right? So it should hold the value of these ones, and when the window slides it should hold the value of some of these, and so on. It should hold the value of some of these, right? um Here I'm finding my value of base, so fixing my value of base. So base should be all the elements which are outside the sliding window, right? Base should be all the elements which are outside the sliding window, like these. So initially the way I had done it was, this is just implementation, you can implement it in a different way. So the way I had done it was base was simply the sum of everything. So then I'm removing everything in the sliding window. I'm going to remove everything in the sliding window from the base. Okay, so for I equals 0, I is less than k, I subtract that from the base. So essentially I'm removing those values from the sliding window. Okay, next what? Next I am adding the values of slide. So what are the values of slide? They will simply be the sum of the first k by 2 elements. Sorry, we skip the k by 2 elements and take the next k by 2 elements, and that is going to be the value of the sliding window, right? Because these are zeros and these will be ones, right? This is for the starting sliding window. Now for the starting sliding window, I just take max of ans plus base plus slide. So this is if we chose this operation, right? Now for each I from k till n, I'm going to slide this window, which means I'm going to remove the ith value from the base, right? I'm going to remove this ith value from the base. I'm going to add this ith value from the base. I'm going to add I minus k value to the base, right? So this is what I'm doing, removing this and adding I minus k value to the base. Then in the sliding window itself, I'm adding the new ith value and removing I minus k by 2 value, right? So that's all this does. Pretty much exactly what I wrote here has been implemented. And then I take maximum of answer plus base as we slide this window, right? Finally, we can return the answer. So that's all for this question, I think. There shouldn't be much doubts. Yeah, you can use prefix sum to solve it as well. It's pretty much the same idea, except instead of using sliding window, you can use prefix sum. Why brute force is not able to solve? Because brute force will become n square, right? If you do a brute force, then for each window you need to sum that window. So basically your time complexity for brute force would be k times n, right? So for each window you're calculating the sum separately, and yeah, even the sides you'll need to calculate so even the base value also you need to calculate. So basically it's going to become big O of n times n. It will be big O of n squared. So that's why brute force does not solve. Okay, so I hope this is understandable. If yeah, so just an intermission, but if you would like, if you would like some support on your CP journey and you feel like you are not able to solve these kinds of problems and you're not sure how to improve, right? Like if you like, there are a lot of online resources available on the internet for competitive programming, but if you feel like you don't know if you're doing the right thing, or you need some order and structured way to do it, like a way to do it which is curated by people who are of higher rating and it's streamlined and efficient, then you should definitely check out Eliminators self-paced courses, which are available on the TLEeliminators.com website. So we have self-paced courses designed for all levels. So starting at very basics for complete noobs, all the way till coders who can solve 3 problems in div 2 rounds. So about specialist level to expert level. We have courses for whatever your level is. Also, each courses covers some amount of topics. For example, the first question today was slightly harder than usual, so it uses the topics of like prefix sum or sliding window. So if you knew those, you could have pretty easily solved this problem. And the courses also contain more than 40 hours of lectures, more than 100 curated practice problems, hints and video solutions, as well as doubt support, which is available in at most like 10-15 minutes. If you ask a doubt, our top rated coder is going to pick it and going to help you out with whatever you're stuck on. So for all this and more, do check out Eliminators self-paced courses. And yeah, okay, we'll move on to the next problem. We'll move on to second problem. Third problem we'll discuss after that one, probably in like 5-10 minutes. Second problem was pretty simple, I think. Yeah. Okay, so we're on the second problem, and the question is XOR after range multiplication query is 1. I'm not sure why this was not kept as the first problem because it's much simpler, but whatever, I guess. You're given an integer array nums of length n and a 2D integer array queries of size q, where each query is equal to some left value, some right value, some value of k, as well as some value v of I. Okay, so for each query, we have to do the following. Start at I equals L, end at I equals R, and we have to do the following update. So nums of I equals nums of I times value mod this 10 to power 9 7. Okay, so we basically each value at every ith step from between L and R, we're multiplying this with this mod, and that's what we're basically doing. Set I equals plus equal to k, and then we have to return the bitwise XOR of all element in nums after processing all the queries. Okay, so that's what we have to do. And here, I hope you understood the question. So here the main thing to note is that n goes up to 10 to the power 3. Okay, so n goes up to 10 to the power 3. Problem B, and n goes up to 10 to the power 3, right? As well as the number of queries also goes up to 10 to the power 3. Now, if you observe this way the queries are going, they basically like, so let's say you have your array of nums, right? You have your array of nums. What is each query doing? It's giving you some L value and it's giving you some R value. And in this block between L and R, and you start at this first position, you multiply it with V, then you jump some K steps, Here also you multiply it with V, and again you jump some K steps, and you multiply it with V, and again you jump some K steps, and you multiply it with V. So at most the number of elements accessed, accessed is equal to r minus L plus 1 elements. Okay, so these are the elements in this subarray which is being touched right now, and at most r minus L plus 1 elements will be accessed when we do this, right? If k equals 1, so if k equals 1, our jump is exactly 1, so then exactly r minus L plus 1 elements will be accessed. And so the maximum value of r is here, the minimum value of L is here, so this means at most L elements will be touched in each query, right? At most L elements, we can do the mod mul in those n elements, right? And the number of queries also 10 power 3. So what if for each query we just directly did the statement, we directly just visited those elements and multiplied? Then the time complexity will be big O of q times n. So q is the number of queries and n is the maximum time it takes for one query. And as you can see, for 10 power 3, this will be big O of, like, number of operations will be in the order of 10 power 3 squared, right? Which is perfectly acceptable. So the solution is simply to directly implement the statement. Okay, the solution for this question is directly implement the statement, and we'll have a look at the code quickly. Okay, and let's see. So for each query, we are finding the value of L. So L is q0, R is q1, K is q2, and V is q3. Now we start I at L and we go I less than equal to R, and each step we do I plus equal to K, right? So that's what the question said over here. Each number gets multiplied with the value v, and we're taking mod, right? So mod is defined as 10 power 9 plus 7. So each step we multiply with v and take mod. Note that here I'm taking long because while doing the multiplication itself, it might exceed the size of integer, right? So nums of I goes up to 10 power 9, v of I goes up to 10 power 5. So in the intermediate step of doing the multiplication, the answer can go up to how much? It can go up to 10 power 9 times 10 power 5, 10 power 14, which will not fit in an integer. So if you do not write this long, you will get a error of some sort, overflow error. So that's why, or you get an incorrect answer because it becomes some negative number, and then you will multiply that, or you'll XOR that. So once this is done, we are simply taking XOR of all elements, which is what they asked, and we're returning that. So that's all for this problem. I think much simpler than the first one because no idea was used, just direct implementation. Okay. Yeah, I guess if you do C with recursive, it will give you TLE. Yeah, second should have been quite easy according to Leetcode. Yeah. Bhalu, the way integer multiplication works is that the value of the leftmost element dominates the way the compiler will see it, right? So if the leftmost element is a normal int and you multiply with a long, it will still be treated as int multiplication only. So if you implement carefully, there won't be any problem in that. And actually, just send your code. I'll have a look at it. If you're just multiplying two longs, it's not going to overflow. Okay. What is my lead code rating? To be honest, I've started lead code pretty recently, so it's not anything that special, I guess. Um, some 2,200, I guess. You can check my profile out, I guess. Um, yeah, without 1ll, it'll be integer multiplication. But if you do long for everything, like if you define that all the numbers and all the queries, like the value of v is long, and the value of nums of I, if you convert it to long over here, then also you can fix the problem, but you're wasting a lot of space. Okay. All right, let's move on to problem C now. I think that there's nothing much to talk about this problem. Yeah. So problem C was on slightly the harder side, I think. Even I took a decent amount of time. Because of that, I could not have time to solve D. And I think 5 points is pretty less for this problem. And also, my implementation is not the cleanest. I think I'm taking more space complexity than required, but still, we'll discuss it. You are given an integer array nums and an integer k. You may repeatedly choose any contiguous subarray of nums whose sum is divisible by k and delete it. So basically, we can choose any contiguous subarray, which means basically normal subarray of nums whose sum is divisible by k and deleted. After each deletion, the remaining elements will close the gap. What do close the gap mean? Basically, like the subarray will remain joined. We're just deleting. There won't be any gap in the middle. Okay. So return the minimum possible sum of nums after performing any number of such deletions. Okay, so we need the minimum possible sum of nums after performing any such deletions, and we can do as many deletions as we want in any order. And the constraints go n goes up to 10 power 5 and k goes up to 10 power 5. Each number is between 1 and 10 power 6. So no number is negative, right? No number is negative. All the numbers are positive. So to get the minimum possible sum, we just want to delete. So that should be kept in mind. Mr. Finisher, there is nothing special about how to get the idea and approach. It's just practice and being used to these kinds of questions. For Bhalu, in your code, you should do the 1ll first. Okay, so it should be like this. It should be like 1ll times nums of I times v of I. okay, times v of I. And the reason is simply because, oh sorry, times v, not v of I. And the reason is simply because the order of precedence will take the left value as the type, as the thing which defines the type. Okay, so the leftmost value is 1, so that 1 ll, so that has a type of long long, so that type will go from left to right. So that's type precedence in C++. Okay, all right. Anyways, problem C. So in this we need some basic knowledge of DP. Okay, how do you identify the question belongs to a particular topic? You have to see the structure of the problem, and if you have done enough questions, you will kind of get an idea. Plus, the if you're completely stuck, there are at most like what, 30 topics in CP. There's not many topics in CP, so you can just think, will this topic apply, will this topic apply? If it's an optimization problem, there's only like 3 techniques max which are used, which is like greedy, DP, or binary search, and stuff like that, right? So you can just think of it one by one, try apply each of them if you're completely stuck. Okay, anyways, so here what we need to do, we need to minimize the value of sum of numbers. Okay, so I will tell you that this question was slightly tricky because I also went down a wrong path while solving this. So I will tell you what is not correct first, right? I'll tell you why greedy approach will fail and why you need a DP approach, and then we will discuss the correct solution. All right, so okay, so basically let's take an example nums array. So let's say nums is 3 1 4 1 5 and k equals 3, right? So yeah, so here we can see that, let's say this is divisible by 3, right? This subarray is divisible by 3. Similarly, this subarray is equal to 9. Its sum is also divisible by 3, and this subarray is also divisible by 3, right? This subarray is also divisible by 3. Its sum is 6, right? um so these are the possible options for the subarrays which we can delete. Okay, so subarrays which look like this, obviously you can have this one as well, but there's no point in doing that. Anyways, so for this, all you simply need to do is delete this whole subarray and you get the minimum answer as 5. Sorry, the minimum value of sum is 5. Okay, so at first, um so first things first, you need to know how to find, you need to know the trick to find subarrays ending at I, ending at I with the with a particular sum, for a, like ending at I with a sum which is divisible by k. Okay, with a sum divisible by k. Okay, so if this is your first time finding this kind of like problem, so you will not know this and it might be pretty confusing. Not knowing this, the problem would become much harder if you didn't know this, but I guess most people should know this trick, that you need a trick to find the subarrays ending at a position I which have a sum divisible by k. So how many people know how to do this sub problem? Okay, so you need to know how to find the subarrays which end at I with a sum divisible by k. Yeah, so you need a map of remainder index. Yes, Anshul explains, that's perfectly right. So the way we do this is, you can either have a map or a vector. Here k goes up to only 10 to the power 5, so only 10 to the power 5 can be stored in a vector itself. But yeah, you need a map from the remainder to the index, and that is the way we find out the subarrays which have a sum divisible by k ending at I. So let me explain what this means. So this is some prior knowledge you need to solve this problem, or at least you need to be able to think of this during the contest. That's why I'm going to explain this first, okay, before getting into any implementation regarding the problem itself. So the way, let's say this is the array, right? This is the array, and let's have a prefix sum. So if you're solving C and the C is pretty decent level, so I hope you know what prefix sum is. So let's say we have a prefix sum on this array as well. Okay, so now let's say if you're at this position I and you want to figure out how many subarrays are there which will end at I and which have a sum divisible exactly by k. Okay, how many subarrays are there which end at I and have a sum divisible exactly by k? I need to figure that out. So basically, what you want is, let's say you have prefix sum at I and this is j. Okay, this is j. Prefix sum at I minus prefix sum at j minus 1, right? So that will be the sum of this thing. That will be this sum. This sum. If this value mod k is equal to 0, then we can say that this whole ij block, this whole block from j till I, that is divisible by k. Okay, so this block is divisible by k if this condition is satisfied. Okay, if this condition, prefix of I minus prefix of ij minus 1 mod k is equal to 0. So I hope this you can understand, right? Is this understandable, for especially for the people who didn't know this from before, like Madhav, Sahil, Balu? Yeah. So prefix of I minus prefix of j mod k should be equal to 0. That means that this sum which is over here is divisible by k. Okay, so now in another way we can say this, is that basically prefix of I. So what was our condition again? Our condition was prefix of I minus prefix of j minus 1, right? Mod k is equal to 0. So basically that means prefix of I mod k, right? Prefix of I mod k is equal to prefix of j minus 1 mod k. And this is the condition, right? This is the condition we need to look for. So basically any j which is there, which has the same modulo, right? Any j, let's say j dash, and it has the same modulo respect to k, like prefix of j dash has the same modulo with respect to k. That means that all of the subarrays till ij or ij dash or jj dash, all of those will be valid. So I hope you guys understood this. Let me just give you an example. Okay, let me give you an example, simple example. Let's say k is equal to 3 and I'll make an array. Let's say 1 2 2 1 2 2 0 0 1 1 1 2 1 2. Okay, some array like this. Let's make the prefix array as well. So this will be 1, the prefix for this. So here we'll only consider prefix mod k. Okay, so we are only going to consider prefix mod k. So 1 plus 2 is 3, 3 mod 3 is 0. Now 0 plus 2 is 2, 2 plus 1 is again 0. Similarly 2, and this will be 4 mod 3, which is 1, and this will be 1, this will be 1, this will be 2, this will be 0, and this will be 1 0 again, 1 0 again. Okay, so this is how our prefix mod k looks like. Now what I said was every time we have, so for every I, for some I, if we can find j such that prefix of I mod k is equal to prefix of j or prefix of j minus 1 mod k, then the subarray I, sorry, j to I is divisible by k. Okay, is divisible by k. So please keep this in mind. The reason this works is because that means a multiple of k must have been added, right? Some multiple of k must have been added to the sum. That's why the value of mod has not changed. So for example, here there's a 2, and well as here there's a 2. Okay, so that means that, what does that mean? That means that the sum of this part is divisible by k, and we can test that. See, 1 plus 2 plus 2 plus 0 plus 0 plus 1 is equal to how much? It's equal to 6, right? And 6 is divisible by 3. So simply by checking whether the mod values at 2 points are equal, then we can tell that this subarray has a sum which is divisible by k. Okay, so is this understandable? Is this clear? Should I repeat it? Can someone put that? I can see people like Anshul and Yash who already knew this. Yeah, okay, I'll explain why greedy fails. um for people who didn't know this, like Sahil, Madhav, Balu, please tell in the chat if you understood this. Right, okay, so this part is clear. This is just a sub problem, it's not the full problem. Okay, Mr. Finisher, you're asking a lot of general advice, so if you want you can save this for the end. Okay, please save this for the end of the session. We'll discuss general advice for CP then. Okay, all right, nice to see. Okay, everyone understood this. Okay, so this is a simple sub problem which we have for the problem, how to find the subarrays ending at I with sum divisible by k. Okay, so now I'm going to give you a greedy idea which is wrong. Okay, so I'm going to give you a wrong greedy idea. Please keep in your mind this is wrong, but this is the basic idea which comes to, I think, everyone's mind after reading the question. But I'll show why it is wrong. And it's not that I'm just showing you a wrong solution just for like that. I think it's instructive to understand how I myself solved the problem. I first got the greedy idea, I got a wrong answer, then I realized the mistake, then I fixed it. Okay, so obviously there'll be people who are good enough to solve it directly, who will know what to solve. But yeah, wrong greedy trap. Okay, so I'm just showing this to help you understand how I figured out that I had to use DP. Okay, so what I did was, my logic was that each time I can find a subarray which is divisible by k, I will remove that subarray. Okay, so if I'm at some position I and I found that prefix of I mod k is equal to some prefix of j mod k, so I can use a map or I can use a vector for this, right? So for each mod, for each value of mod, I have a vector mod k, I have a vector, right? Because k only goes up to 10 power 5, so I can just make a vector. Otherwise I would need something like a map or unordered map. So for each value of mod k, I have a vector and I store it. And in that vector, if I see that there is some j already which satisfies this, that means I can delete this subarray, right? I can delete this, right? So I thought about doing this, like repeatedly deleting um the maximum j, like maximum size I could get, right? And yeah, so if there are multiple j, let's say there are multiple j, right? Let's say there are multiple j which satisfy this condition. So let's say this is j and this is j dash, and this is j dash. So which one should I pick, right? So I thought I'll always pick the larger one. So if I have a choice between this and this, I'll pick the larger one and delete that. Okay, so the way I um implemented this was, for each value of mod, I will store the first point which that mod appears. Then I will go from the back. So go from loop from n minus 1, loop from I equals n minus 1 to I equals 0. And let's say I'm starting off at this position and I will go back. And then here I see that, let's say this has some value of x mod k. And let's say this has some value of x mod k. Okay, so this is the first point where x mod k appears. So I'll jump from here and I will keep adding values. Okay, so I will skip all these values, I will not add them to the answer. Then again, let's say here the value is y mod k, and here also the value is y mod k. So again I add these values, but I will jump here and I will not add them. So basically I've deleted these values in the middle. Okay, so this is a greedy idea, but yeah, I always take the min j locking in. But the reason this doesn't work is, yeah, the reason this doesn't work is that there can be overlapping intervals which have the same sum. Okay, so there can be overlapping intervals which have the same sum. And let me show you a counter example. So let's say k was let's say k is 20. Okay, so k is, or maybe k is something. Okay, let's say k is 20 only. And let me just make a example array to show you exactly what's going wrong. So let's say we have 17 here, and then let's say we have so give me a minute, I'm making the example right now. So we have 17 here, and we have 23 here, and we have 15 here, and we have, let's say, 25, or we have 5. Give me a sec. Okay, so basically what I'm trying to make is an example where we have like two intervals which overlap. Okay, so the whole interval sum is not equal to, is not divisible by 20, but the left part and the right part are both divisible by 20, and basically we are choosing the wrong part out of them. Okay, so for example, so let me just make the example. It's a bit tricky to actually make examples, so give me 2 minutes. um, yeah, okay, so I think we've got an example. Just give me a sec. Yeah, so we have an example here. All right, so here if we run our greedy strategy, what happens? Okay, so we start at 3, right? We start at 3, and um okay, wait, no, let's say this is 10. um okay, wait, actually I can just show you the lead code example for this as well. So it's a bit hard to construct this. um yeah, I can just take the example from my wrong answer itself, or just give me another minute, I guess. 3, so this will be 23, and I can split 20 minus 3 in here, so that's 17, and the sum of 17 in here. So I'll split this into 5, and let's say 12. 12 plus 5 plus 3 is 20, right? And this will be 14 minus 18, 13 minus 7, which is 23. Okay. All right. So yeah, I think this is a decent example. So for k equals 20, let's say we have the array 23, 12, 5, and 3. Okay. So let's try a greedy strategy on this array. And if you try the greedy strategy from the end, um, if you try the greedy strategy from the end, you get the sum of 12, 5, and 3, right? And this is divisible by 20 because 12 plus 5 plus 3, 12 plus 5 plus 3 is divisible by 20. This equals exactly 20, right? So what the greedy strategy is going to do is it's going to remove this from the array, then it's going to see 23, and that is the only value remaining. So it is not divisible by 20, so it's going to return 23. Okay, but the actual solution, the correct solution is to remove the values 23, 12, and 5, right? If you remove the values 23, 12, and 5, these will sum to 40, these will sum to 40, and the remaining value is 3. So I hope you understand. So basically it's better to remove the 40 rather than remove the 20, but because these two intervals were overlapping, right? Because these two intervals were overlapping, so this interval was overlapping with this interval. And if you do a greedy strategy, either the first or second one will be taken, right? But basically we need to consider both the ways of taking and see which one is maximum, right? So is this understandable, guys? Yeah, so this is the example. Please try it out. The example is k equals 20. We have four elements which are 23, 12, 5, and 3. Okay. The greedy strategy takes the first subarray which it can see, like from 3. Um, the only value which gives us a divisible of 20 is 12, 5, and 3. But the correct way to do it was take 23, 12, and 5. Right? Yeah. So when this greedy strategy fails, right, what we're going to do instead is we're going to do a DP, right? We're going to do a DP. Um, so actual solution, let's write it down. So actual solution. So again, let's just summarize what we did so far. So first thing we did was see the subproblem of how to find subarrays ending at I with the same divisibility by k, right? So this is to simply check if the remainder is same in the prefix mod k array. So that was what we first discussed. Then the second thing was this greedy trap. If you do a greedy value check, while it looks correct, there are some test cases like this test case where two intervals are overlapping. We don't know which one to pick, and those might affect the answer, right? So that's why we get the idea that since we don't know which one to pick and we have some choices, we should do some kind of DP, right? So that's how I understood that the question is DP. So the actual answer is do a DP on the choices available, right? Do a DP on the choices available at each step. Okay. Dhanush, no, your idea is your that idea is also incorrect because you can't remove the subarray with largest sum divisible by k, because again you might run into problems. Like for example, if you have, let's say this is the largest subarray which is divisible by k. So let me give you an example for why Dhanush's answer is wrong. So if you have an array like this, and let's say this one is the largest one which is divisible by k. Okay, but there are some smaller ones, like for example this one and this one, and let's say this one. Okay, and all of these are also divisible by k. Now what happens in this case is you will take the largest one greedily, but if you instead took these three, then some of these three could have been greater than the largest one, right? The sum of these three could have been greater than the largest one. So that's why your answer would also fail in this case. Okay. Knapsack of intervals. The reason knapsack of intervals will fail, Sai Chandra, is because the number of intervals possible might be very large. So it would become big of n square to make a knapsack of intervals. Okay. So now we're going to do the actual approach, which is do a DP on the choices available. And for this, we'll need some math. So pay attention. This part is also not very easy. Okay. This part will also be taking some concentration. Okay. So again, let me draw an example array. and let's say I am at some position I, right? I am at some position I, and my dp of I is, I need to find the value of dp of I, which is the maximum sum which I can make. So we need to minimize, we need to minimize the total sum of the array, right? We need to minimize the total sum of array. So we need to minimize total sum of array, total sum of array. So we can write this sum or sum as total sum minus values which are removed. Okay, values which are removed, right? So we can write this as total sum minus values which are removed. So basically we will find this maximum value to remove, and that will give us the answer, right? We need to minimize the final sum of the array. So basically what I'm going to do is my dp of 5 is going to be the maximum value removed. Okay, so that's why dp will not be minimum, dp we're trying to find maximum, and this is just for convenience. Okay, so my dp of I, dp of I will be maximum value I can remove, value I can remove, I can remove in 0 to I. Fine. So that's what my dp value is going to be. All right. So now at position I have two options. Okay. So I hope you understand what my dp state is. My dp state is simply dp of I equals maximum value I can remove, I can remove under the given operation, under the given operation in the range 0 to I. Okay, so that's how dp works. We calculate the sub problems like 0 to I dp, so on, and get out the answer. Okay, now we're going to think about how to do the transition for this. All right, so I am at some position I, and either I simply don't do any operation here, right? I have two choices. I can either do an operation, my choices, if we're thinking of the algorithm itself, right? We're thinking in the perspective of the dp algorithm. So when I'm at position I have two choices: either do nothing, either do nothing, or pick one of the valid j, or pick one of the valid j, one of the valid j, such that such that um basically such that prefix of j, such that prefix of j mod k is equal to prefix of I mod k, right? Prefix of I mod k, or to be technical it should be j minus 1, but yeah, this is basically the idea. Let's say there's some j over here, so then this value which I get, um I can remove that, right? So I have these two choices. So this much is clear, everyone? This much is clear. I have two choices when I am in my dp, so that will define my transition. Okay, so my dp of I is the minimum value of I, maximum value of I, which I can remove in some range, and I have two choices: either I do nothing or pick some valid j and delete that valid j. Okay, and then I can move on to the next value. Okay, so this much is clear. So for the first case I will simply set dp of I equals dp of I minus 1. Okay, so if I do nothing, that means that I'm simply, ignoring this. So then my value will be whatever the value I have of dp of I minus 1, that will be my answer. Okay, whatever max I can remove in them if I have to do no operation here. Now for the remaining, um what I want to do is find all j, find all j such that prefix of j, mod k is equal to prefix of I mod k, and I can update like this, I can update like this. I can write dp of I will be max of dp of I plus, sorry, dp of I will be max of dp of I, or dp of j plus prefix of I minus prefix of j. Okay, so I hope you understand this. The reason for this is when we are deleting these elements, we are deleting these elements from the range I to j. That means we need the sum of the elements here, right? We need the sum of the elements here. So these elements which are getting deleted, that is equal to prefix of I minus prefix of j. Okay, this is equal to prefix of I minus prefix of j, and this is this sum. And then over here, whatever dp of j is there, that also we are considering. Okay, so basically, in case we choose to delete, the deletion will mean that we have deleted all the elements from I to j, and since those elements are removed, they will be added to the dp as well as dp of j, which means that now that we have deleted this interval, we need to find the max deletions here, right? So that's why we have this transition. Yes, it will lead to n square. It will lead to n square. So this code will be big O of n square, because all these j might be many positions, right? There may be many j's which are satisfying this. So this idea is big O of n square, but I'll tell you how to optimize it. But for now, I just want you to understand that this is correct, right? Like, do you get the idea? For now, I just want you to get the idea. This is n square only, because for each I we are finding all these j, and for each of them we're doing an update. So this idea is n square right now, but at least the idea is understandable, right? If I directly tell the big O of an idea, it might be get confusing. That's why I'm telling this first. Okay, so I think this is clear. The simple reason is, when we find an I and j, we can delete this interval, and then for the remaining we can do gp of j plus that. So then this is the sum. This is the sum of the values in the I and j, and this is the dp value of j, and that's why we have such an equation. Okay, so now we want to do this transition in big O of 1. Okay, instead of this, all j could be big O of n transition, right? This transition could be big O of n time, so the overall time would become big O of n square. We want to do the transition in big O of 1. So again, we will carefully inspect the transition. Okay, so the transition says dp of I equals max of dp of I, and what I'm going to do is I'm going to rearrange these variables. So it's prefix of j plus dp of j minus prefix of j. Okay, so the values which are coming from j, the values which are coming from j is only this portion. Okay, these are the portion which is coming from j. Okay, so for each valid j, for each valid j with same mode, with same mode of pref, right? So this is the only thing which comes from j, right? This value dp of j minus prefix of j. So instead of checking each and every one, what I simply need to do for this transition is to store the maximum j for each mod, where this, for each mod I need to store the maximum j which has maximum value of dp of j minus prefix of I. Okay, so that's all I need to do for each mod. If I store the one which has the maximum dp of j minus prefix of j, I can simply add that instead and not do big O of n time. Yes, yes. So we need to keep track of max of dp of j minus prefix of j for each possible value of mod. For Madhav, you want to explain the transition, right? So the transition here basically is, earlier we had discussed how to find the values which have the same remainder as I, right? If we find those values, we mean that that interval has the sum divisible by k. So that's what we discussed earlier. So we're using that idea and we're saying, for each possible value j, which has the sum of j to I is divisible by k. So for each of those values, we will do this dp update. And why is this dp update working? It's because dp is showing the maximum value to remove, right? So if we remove the values I to j, that means that prefix of I minus prefix of j is removed, basic prefix sums, and in the remaining value we're taking maximum of dp. So that's how this transition works. Okay, so if you find any step confusing, just rewatch that part of the video. Use pen and paper. I think you'll understand that for each j we're considering that step, and this is what happens according to that step. Now, because this solution is big O of n square, because the transition is itself taking big O of n, we are reducing this to big O of 1. And how are we doing this? Basically, each value of j only depends on this value dp of j minus prefix of j, right? So we simply need the max for each mod for each mod value, we simply need the max of this, right? Max of this for each mod value. For each mod value we will store. Okay, so we will store this. We will store this. Okay, so I'm going to show the code for this, which might clear this up. Not code, like pseudocode. So basically we'll have a DP array first. So let's have a DP array first, which will be, let's say, size n, right? Okay, so we'll have three arrays. Okay, one will be DP, one will be the prefix sum, and one will be the or let me, instead of writing it, I'll just write it as pseudocode. Okay, so pseudocode, and imagine we have a prefix sum array, so that should be simple enough. Prefix sum, imagine we pre-computed the prefix sum, so pre-compute the prefix sum for all values, for all positions. So that's simple, big O of n prefix sum. Then we also have an array DP. In the start, we'll set all the values of DP to 0, right? We want it to be maximized, so DP of size n values all set to 0. And we also have a value best, which we are going to set to negative infinity, n values. Okay, n values set to negative infinity, and this array is called best. All right, so all negative infinity, fine. And also one more thing to note, since when we're starting out, yeah, so what not, these will be k values, sorry, k values, right? So what will this store for each value of, for each mod with respect to k, it will store max value of dp of j minus prefix of j. Okay, if prefix of j mod k equals x. So basically for each mod x with respect to k, it is going to store the max value of dp of j minus prefix of j if prefix of j mod k is equal to x. Okay, so this is what the best array is going to store. Now what we're going to do is simply for each I, for I from 0 to, let's say, n, right? For I from 0 to n minus 1, what we're going to do is we're first going to update the dp. So first dp transition is simply to keep it n minus 1. So dp of I equals dp of I minus 1. And now we're going to do the second dp transition. So let x equals prefix of I mod k. Okay, so then we can say dp of I equals max of dp of I, comma this thing, right? So comma prefix of I plus the maximum value of dp of j minus prefix of j. So we can say that as the prefix of I plus best of x, right? X is the all the values which have prefix of I mod k as the same as this one, right? So that's what we're going to do for the dp. And then simply in the end we can return total sum minus dp of n minus 1. Okay, so that is the answer we're returning. That's going to be the final answer, which will be total sum minus dp of n minus 1. And also please note that best of 0 has to be set to 0, because if we want a remainder of 0, if we want a remainder of 0, then we can simply pick no elements in the start, right? So that's why best of 0 will be set to 0. All the other values will be set to negative infinity. Okay, so basically this is the solution. It's pretty much exactly what Anshul explains said. We need to keep track of maximum value of dp of j minus prefix of I. So let me just summarize what we did. Again, first thing which we discussed was this sub problem, which was how to find subarrays ending at I with a sum divisible by k. For that, we noted that the prefix of I mod k should be equal to the prefix of j mod k. Okay, so that's how we find the subarrays which have sum divisible by k, they must have the same prefix value. Now we discuss why the greedy approach is wrong by simply taking the maximum one with that same prefix value. And now we're going to see the actual answer, and the actual answer is simply, we have some, let's say, n choices available to choose which j we are choosing, right? And based on each of the choices, we have a dp transition. So dp of j plus prefix of I minus prefix of j, right? Because if we delete these values in middle, that is going to be prefix of I minus prefix of j, and the remaining values will sum to dp of j, right? So that's how much which options we have, and we're updating dp of I with that. Now this transition would take big O of n square, like this whole code would take big O of n square. To make it big O of n, we are noting that we simply need to find the maximum value of dp of j minus prefix of j for all the j which have the same prefix mod, right? For all the j which have the same prefix of mod, we need to find the maximum value of dp of j minus prefix of j. So we will store the max for each mod value. We are storing this in an array called best. For each mod value from 0 to k minus 1, basically those will be the mod values, right? This will be the mod value 0, this will be the mod value 1, this will be the mod value 2, all the way till mod value k minus 1. We are going to store the mod maximum of dp of j minus prefix of j. And yeah, so our code is going to be best of 0 is 0. For each I, we are updating. Oh yeah, we should also update the best value. So let me just write that as well. So dp of I will be equal to I minus 1. X is the value prefix of I mod k. So dp of I gets updated with that best one. And also best of x should also be updated to be equal to max of best of x, and dp of I minus prefix of I, right? So this is the updation of best for the mod x value, right? For all the values which have prefix mod x. So basically this is the code for it. So the code is not that complicated, although I wrote it in a bit complicated form in my actual implementation, because of, in a contest you're in a hurry, so you're not clearing up your code that much. But the basic idea is only this much. But yeah, the idea going behind this is pretty decently complicated. It's a pretty advanced, not that advanced, but pretty decent level dp. What would be the rating of this problem in cf? I guess this would be pretty decent dp. So it's like maybe 1700, maybe 1700 on cf, I would say. Okay, so I'll explain through the code. N is obviously the size of the vector. All right, so this is going to store the maximum value of dp of j minus prefix of j for each mod. Okay, for each prefix of j mod k. Okay, so this is what best stores. Prefix is simply a prefix sum array. So prefix is simply the prefix sum array. And dp is simply the value which I defined for dp. So here I said that dp is the max value I can remove under the given operation in 0 to I, right? So basically answer for 0 to I, max removable sum in for 0 to I. Okay, so this is what the definition of best dp and prefixes. Here I'm simply computing the prefix sum, nothing much to explain. Also dp of I will be dp of I minus 1, prefix of I will be increased by prefix of I minus 1, that's all. So this is just the base case for the dp, the simple transition. Now if this value existed in best, right, if this value existed in best, that means that prefix of I mod k has been set in best, right? Initially it's set to negative infinity. If it's not equal to a negative infinity, then I will do dp of I equals max of dp of I comma prefix of I plus best, right? So what is this? This is simply prefix of I plus dp of j minus prefix of j, right? And by using best of this mod value, basically I'm finding the maximum sum of dp of j minus prefix of I, right? So I'm basically finding max of this over all valid j, over all valid j, and I'm doing this in O of 1 instead of O of n, right? So that's why this line, now I'm updating best of prefix of I mod k. So I'm updating best of prefix of I mod k, and that's simply the max of what it was already, and dp of I minus prefix of I. Okay, so that's how this works. Akshit, if your approach, if you write a summary at the end of the session, so we still have to discuss D. So once we discuss D at the end of the session, if you write a summary, I will do it. How to see these types of patterns in question of DP? Well, I try to explain how I thought of it logically, like step by step. So you can rewatch the video. First, I solved this sub problem, which I also did like during the contest mentally. I remembered this because I already knew this. Then after that, I tried a greedy approach. It was giving a wrong answer, and it, because Leetcode shows test cases, I could quickly see the wrong answer as well. And it was because of these types of test cases, right, where you're not able to choose between intervals. So then I thought of a DP approach. Basically, I was like, if greedy is not working, I can't simply choose the maximum length interval. I need to find which interval works. So then I had this n square approach for each of the intervals, right? And then I optimized the n square approach by noting that we simply need the maximum value of dp of j minus prefix of j. Okay, so that's how I solved this problem, and I simply stored that value. How to solve these types of patterns? Well, to be honest, if you have seen this pattern, like this question now, and you solve it yourself after the stream, I think this kind of idea you'll get used to pretty quickly. It's not like, okay, see, Govind, everyone has a different level, right? Like, it doesn't depend on which year you are or stuff like that, or even your age. There are people who are in 11th grade and they can also solve these questions better than me. So it's more about how much time you spent and how much um practice you did. There's nothing else. All right, I hope this is understandable. If it was not, do revisit the code and do revisit the explanation. um yeah, I think, Madhav, the main problem you're having is you're not understanding the transition, right? The main thing about the transition here is simply, so this is for Madhav. If you're here, um pay a bit of attention. What I'm trying to say over here is basically, if you're at some position I and you want to calculate the dp of I, you want to calculate the dp of I, which is the maximum amount we can remove, right? Which is the maximum amount we can remove up to I. So let's say we find all the valid subarrays we can remove. So this subarray has a sum which is del by k. Okay, so this is some j. Then that means that we removed this subarray. And how much is that? The sum of this can be found using prefix sums. That is simply prefix of I minus prefix of j. Right, so we removed this interval we removed. Now in the remaining values, we can still remove, right? We can still remove. So that will be simply computed by dp of j, right? That will be simply computed by dp of j. So that's why the dp transition is dp of I plus prefix of, sorry, dp of j plus prefix of I minus prefix of j. That is why the dp transition is like that, Madhav. Now the contribution of the j part is simply dp of j minus prefix of j. So we can reduce it to big O of 1 by simply showing the max value of that. Anyways, for general advice, we'll address it at the end. We have to now discuss problem D. Okay, so we're going to go to problem D now. And problem D is, I think, less tricky, more about knowing the concept. So just give me 2 minutes. I'll go drink some water and then we'll continue with problem D. And then after that, we can take general doubts. Okay, before we start problem D, one thing I will note is prior knowledge. I'll just write down prior knowledge required. Without this, you will not be able to solve. And problem D is, I think, easily code forces 2000 at least. So prior knowledge required is inverse mod multiplication, right? So you need to know either you need a template, or you need to know how to do inverse mod, which means basically modular division, right? This basically means modular division. And the second thing you need to know for this problem is basic ideas of square root decomposition. Okay, square root decomposition is a pretty advanced topic. It's not, I think, even covered in TLE's course as far as I know. Let me just check. Yeah, I don't think they cover square root decomposition. So you need these two ideas roughly for this problem, and we'll just get started with it in like a minute. All right, I'm back, and we'll get started with this problem now. The question again, as lead code problems are pretty straightforward, is the same as the second question, except the constraints are changed. The constraints go up to 10 to the power 5 for the length of the array, as well as 10 to the power 5 for the um, number of queries, right? So the number of queries and the length of the array have been changed to 10 to the power 5, and that's the only difference. So n square solutions will not work. Okay, so n square solutions are not going to work, and that's the only difference. We need to solve it in n, big O of n, big O of square root of n, big O of n log n, something like that. Okay, we need to solve it in um need to solve in big O of, let's say, maybe n plus q log n plus q, n plus q square root of n, something like this. We need to solve it in. Okay, all right. Okay, Manav has some doubt in question C. Let's just quickly see that first. I have an array A, B, C, D, E. When I was at D, my best was to remove B, C, D. No, see, the best array is simply, you need to understand what the best array is storing. It is not actually removing anything. The best array is simply storing the maximum value of prefix of j, of dp of j minus prefix of j. So in this case, it will simply store um, dp at b minus prefix at b. Okay, so it would store the dp at b minus prefix at b, or sorry, to remove bcd, it will store the prefix of a minus dp of a, right? Sorry, dp of a minus prefix of a, and that is what is the maximum value at that point, and it won't change. So yeah, you don't need to change the best array again. To understand, I think this question, you need to write down the dp equation on pen and paper, and then you need to try it out. Like take the code, take a pen and paper, write it down and understand, because I don't think you can understand this directly just watching a video. Okay, so for problem C, please do that, especially people who are stuck in it. Okay, so in problem D, we need to solve it in roughly this much time complexity, and this is the prior knowledge I've already told you. So if you don't know any of these topics and you still want to solve problem D, go read up on them. Okay, and obviously you need to understand like basic modular math, but if you have made it this far, you will, I hope you understand basic modular math. Okay, right. So for each query, let us revisit what we are doing. Okay, so for each query, let us revisit what we are doing. Basically, we are starting at some position L. We are starting at some position L, and we are going to some position R, and let's say our K was equal to 3. So that means we're going to add 3. We're going to go to this position, right? We're going to add 3 again. 1, 2. Okay, wait. 1, 2, 3. So we're going to go to this position. Then we're going to go to this position. Then we're going to go to this position. Then we are going to go to this position. The next one takes us outside, so we don't do anything. So these are the values which are getting affected, and these are the values which are getting multiplied by 3 or multiplied by V, right? So this value gets multiplied by V, 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 this value gets multiplied by V. So this is what each query is doing. What each query is doing, right? So just a refresher, what each query is doing. Okay, so let's say the number of elements accessed is less. So we are basically going from L and R, and we're doing jumps of size K. So let's say these jumps were large. Let's say K is large. Okay, K is large. Then the jumps will be big jumps, right? The jumps will be big jumps if K is large, and they will only change a very few values. They will only change a very few values. Meanwhile, if the jumps were small, let's say the jumps were like size 1, 2, 3 jumps, then they will edit a lot of values, right? They will edit a lot of values, right? So K is large is fine because that will not take much effort plus query, but K is small. We need to find some way to handle this, right? Find some way to handle this case. Okay, so I hope you understood this part, that if K is large, then the jump sizes are large, so the number of elements which are being touched is not much, or number of elements being accessed is not much, so there's no problem. But if K is small, then there are a lot of elements being changed each query, so we need to handle that somehow. Okay, so now let us consider this approach. Okay, so observation, let's write some observations. So first observation, when starting at L, going to R, and making jumps of K, making jumps of K, we are visiting the values, L, L plus K, L plus 2K, L plus 3K, so on to L plus xk, such that this L plus xk is less than R, right? L plus xk is less than R, right? So this is what the query is doing. Now, in the observation we need to note here is that the I, let's say I value is first L, I is going to L plus K, L plus 2K. I mod K is not changing. Okay, I mod K is not changing, right? Basically, it's visiting all the values which are I mod K. So for example, L mod K will be equal to L plus K mod K, right? So this much so you will know, equals L plus 2K mod K, so on, right? So basically it's visiting those values which have some specific mod L mod K with respect to the array, right? So let's say if the whole array had, let's say, 12 elements. Okay, the array had 12 elements, so 1 2 3 4 5 6 7 8 9 10 11 12. Okay, so this array had 12 elements, and let's say for one query K is equal to 3, then this will have 0 mod 3, 1 mod 3, 2 mod 3, 0 mod 3, 1 mod 3, 2 mod 3, 0 mod 3, 1 mod 3, 2 mod 3, 0 mod 3, 1 mod 3, 2 mod 3. Okay, so these are the different mod values with respect to 3. Now let's say we had a query which goes from L equals 2, R equals 11, or maybe R equals 10, and K equals 3, right? And V equals 2. So let's say all the values were 1 in the start, and we want to see what happens with this query. So basically what's happening with this query is we start at position L equals 2. So that is this position, right? This is the position L equals 2. And we have to end at position R equals 10. So this is the R equals 10, L equals 2. Now each time when we do a jump, we are jumping to a place which has the same mod value, right? So this, then we're jumping here, then we are jumping here, then next time we jump we go outside, so we're not jumping over there, right? So these are the values which are getting multiplied by 2, right? These are the values which are getting multiplied by 2, right? I hope that makes sense, that this is what we're doing. So basically, instead of manually doing this, what if we had a prefix multiplication array? Okay, so what if we had a prefix multiplication multiply multiplication array? Okay, so what if we had a prefix multiplication array? And basically the way this multiplication array is going to work is that let's draw 12 elements from before. Okay, let's draw 12 elements from before. Let me just draw 12. So 1 2 3 4 5 6 7 8 9 10 11 12. Okay, and sorry, this will be 12 elements, right? And let all the values be 1. So 1 2 3 4 5 6 7 8 9 10 11 12. So this was the array initially. Now again let me note the values which have mod 2 mod 3. So let me just mark those values which have 2 mod 3. So this value, this value, this value, and this value, right? All these values have 2 mod 3. So keep them in mind. Now when we do the query, query occurs, right? So what we're going to do is we're basically going to edit the prefix value over here. So assume that this was a prefix array. Assume this was a prefix array, prefix multiplication array, and the query occurs. Then let me just actually let me just copy this and we can see what happens. Okay, so assume this was a prefix multiplication array. Let me just make a copy of this. So right, assume this was a prefix multiplication array, and what we're going to do here is we're going to, so this is the value of L and this is the value of R, right? That was what we discussed. So let's say L equals 2, R equals 10, V equals 2, K equals 3. Okay, so here what we'll do is we'll multiply this with 2. Okay, we won't touch any of them in the middle, and here we'll multiply this with half. Okay, we'll multiply this with half. Fine, for now just keep it in mind half. What we actually mean by multiplying in half is modulo inverse of 2. We're going to multiply with modular inverse of 2, but for now we're going to represent it as half. Okay, so imagine we did this, and then what will our numbers look like? Our numbers are going to look like 1 1 1, sorry, 1 1 2, 1 1 1, or let me just paste that array again and change it, right? So after this query, our array is going to look something like this, and this one will be 2 over here, this one will be 2, and then this one will be half. Okay, so this is what our array is going to look like. And then after all the queries, queries are over, we will do prefix multiplication over this array. Okay, so we will do prefix multiplication over this array. So what does that mean? It basically means so we had over here half, right? So just give me a sec. Oh wait, right, let me just remove this. We had here 2 and we had here half. Okay, so we had here 2 and we had here half. So what I'm going to do here is so what does prefix multiplication, we're doing this respect to mod, right? So this value will equal multiplied by 1. Similarly, this value will become equal to multiplied by this value. This value will become multiplied by this value, and so on. So when it comes to the values we care about, which have mod 2 with respect to k, these are mod 2 with respect to k, right? So then this will become multiplied with this, so this will become 2, right? This will become 2. Just give me a sec. This will become 2, and similarly this is going to become 2. Okay, and the last one is, we're going to see what happens to it. So this becomes 2 and this becomes 2 because it got multiplied with this. Similarly, this got multiplied with this. Now here this was equal to half, right? This was equal to half. So what happens to it? We multiply 2 with half and it becomes 1. Okay, it becomes 1. And basically this becomes 1 over here, right? And this is the final array after all the queries are processed. So as you can see, right now in this example, there was only one query. And instead of manually going through these values and changing them to do, what we did was we made the value at L, we multiplied with 2. And also the next value which just comes after R, the next value which just comes after R, we multiplied with that half. So when we do a prefix multiplication over this, exactly the values which we want have become 2, right? So I hope this made sense. I'm not sure how much you're following. So can someone tell in the chat if you're following this? So this is for some particular k. Let me just note this down. For some particular value of k. Value of k only. We made this prefix array. Each query LR k v prefix of L will be multiplied with v, and let x be next value after R, where let x be the next value after R, where L mod k equal to x mod k, and that value also, that value we will divide with v. Okay, then finally do prefix multiplication on the numbers. Okay, finally do prefix multiplication for pref. Okay, for pref, but with respect to the mod, right? For pref. So if the mod is same, then it will be multiplied with the previous value. So pref of I will be multiplied with basically pref of I minus k. Okay, so this is what we are doing. Yeah, so this is how this example works. But the problem with this is for each k, we'll need to make a new prefix array. Okay, so the problem with this approach is for each k we will need to make a new prefix array, and that is a problem because k has total 10 to the power 5 possible values, right? K has total 10 to the 5 possible values. Where is k? Yeah, k goes up to n. So k goes up to n and goes up to 10 5. So each value of k has about 10 to the power 5 values. I hope you understand that. Yeah. So obviously we cannot create 10 to the power 5 different arrays of size n. We won't have time complexity nor the memory complexity to do that. So how to solve the problem? Okay, how to solve the problem? And basically what we're going to do is we're going to do a technique called square root decomposition. Okay, so the technique will be used here, square root decomposition. So basically for some values we will use the first technique, and for other values we're going to use the second technique. Okay, so basically like I said, for large values of k in a query which has large values of k, it is fine to access the elements since only very few elements are getting accessed, right? So we will choose some threshold b. Okay, so we'll choose some block size or threshold size b, choose a threshold value b. Okay, then if k is greater than or equal to b, okay, if k is greater than or equal to b, we will directly do for each query. Okay, so this is for each query. If k is greater than or equal to b, directly do the operation on nums. Okay, do the multiplication on nums. So directly do the multiplication on nums, right? Otherwise, else k is less than b. So we will have b different prefix arrays. So we will put it in the corresponding prefix array. Okay, we'll put in prefix of k, l will be multiplied with. So we have b different prefix arrays for each mod value which we are storing. We will have a different prefix array. So for each prefix of k times l, we will multiply it with v, and prefix of k r plus that remaining value. So we need to find some value which is greater than r, which has the same mod as l, right? So let's call it x. Will be divided with v. Okay, where this is mod division. Now for each number, once all the queries are over, we need to update the value of nums, right? So it's only stored in the prefix arrays. We need to store it in the num array also. So basically for each prefix array, for each, let's say I from 0 to b, prefix of I. So basically we'll have something like nums of I, prefix of I, also for each, let's say j equals, let's call this for each j from 0 to b, and let's call this from each I from 0 to n. And we will write prefix of j. So this is the jth mod we are considering, and this is I. So we're doing the prefix multiplication here. So we're going to do prefix of j times I, j of I equals prefix of j I minus k. So this is the prefix multiplication, and then we're also going to multiply nums I with this. So nums I will be equal to prefix of j times I. Okay, and then once all of this is done, we can simply find XOR of all elements in num. So find XOR of all elements in num and return it. So that's just the simple, just find XOR of all elements in num and return. Nothing much to think about that, right? And that is the full solution to this problem. And what is a good threshold value? You can show that somewhere around big O of square root of n is a good threshold value. That's why we call this square root decomposition. And let me just tell you the time complexity analysis. So if this is your first time seeing square root decomposition, it might be a bit hard to understand. But the time complexity for this will be, so in this part, when we are processing the queries, so this part is processing the queries, right? Processing queries. So if k is greater than or equal to b, then we're directly doing the multiplication, right? So we're directly doing the multiplication means it will visit, let's say, jumps of size b, right? K is b, so jumps will be at least size b. So the maximum number of jumps or number of access it has done is n by b, right? So the maximum number of access it has done is n by b. So for each query, it can take n by b time. Okay. What about the second one? If k is less than b, then it's simply changing two values. So this is roughly big O of 1 or big O of b, depending on how you implement it. Let's just consider it as big O of 1 for now. So it'll be q times n by b. Now for each value of b and for each value of n, we are updating the prefix, we are calculating the prefix multiplication, and we're also updating the value of the number. So that is big O of n times b, right? And finally, we are finding the XOR of all elements and returning that. So that's big O of n. We don't need to count it. That's just a small big O of n extra, so that's not needed to be counted. Okay. So this is the total time complexity. Now if you choose b equals square root of n, you can see that this will become big O of q times n divided by square root of n plus n times square root of n, right? And let's simplify this. We get big O of q root n plus n root n, or the time complexity becomes big O of n plus q root n. Okay, and this is a valid time complexity for 10 to the 5, right? N and cube go up to 10 power 5. As you can see in the start also we discussed that n plus q root n is a valid time complexity, which we get using the square root decomposition approach. Okay, so basically we have two methods for large k and small k. For the large k method we directly do it. For the small k method we use a prefix multiplication approach. That's all we are doing. And both of these methods separately will take n square, but when we combine them in this unique way, they take big of root n root n, right? And if you want to verify, you can see that the time complexity for this is n plus q plus root n is like it satisfies, right? So we can write let's just write n root n, and let's set n equals 10 to the power 5, and this is roughly 3 times 10 power 7 roughly, so it fits, right? Why is segment tree not applicable? You can do segment tree as well. You can do k different segment trees, but that will take extra log factor. That's why we're simply using a prefix array instead of segment tree, since the values themselves of numbers are not directly changing, right? That's why. What software do I use for writing? This is not OneNote. This is External plus plus, which is a open source, I think, Linux writing like journal software. Yeah. Okay. Yes, you can apply segment tree, but there will be additional log n factor. So you will need to make k different segment trees. You'll need to make b different segment trees. So if you use seg tree, it's gonna be additional big O of q root n. Each query will be q root n plus log n, and it will become n root n log n, right? So this is what happens if you do segment trees. So you can still use segment trees, but since we don't need to change the values, we just need to do multiplication. We can use prefix array instead. And prefix array is simpler also. And segment tree will also take memory, have large memory overhead comparatively. So we don't need to do updates. We just need to do this range prefix additions, right? So that's why it's better to do it this way. Okay. Yeah, as well as space complexity. Space complexity for this will be, so we're making b arrays each with n values, so it'll be big of b times n, which is roughly big of n root n, right? In fact, your b does not strictly need to be root n, even like b like 200, 250, 300, 400, as long as it's fine, it will work. So this is the approach for the problem. Basically for large k we're using direct approach. For small k we're using the prefix array approach. In the end we have to update all the prefix arrays, and we have at most root n different prefix arrays, and at most root n access for the large approach. So that's why this whole thing works in big of n plus q root n. All right, so kind of direct square root idea, square root decomposition type of ideas. Okay. So let me just go through the code once quickly. M is the modulo. I'm just keeping the mod calculations in LL so that we don't have overflow. And this is a template I have for modular multiplication, exponentiation, inverse. Okay, so I just put this in because we need mod inverse, right? We need mod inverse. That's why I copied pasted this. Copy pasting templates I think is fine on Leetcode. So yeah, I copy pasted this template for mod inverse. Okay, so this calculates basically, like I said, while doing the prefix array, we need to multiply, like divide the value over here, right? We need to do prefix of x divided by v. So this is to simply calculate the mod inverse over here. Okay. Now we have the problem XOR after queries. This is the function. This is my threshold value b. So you can set this to square root of n, but I just set it to 300 by default. Like, why not, right? I didn't want to write square root of n. Obviously you can set it to square root of n as well. N is simply nums.size. This is my array of prefix values which I've called mul. So I have b different arrays, b different prefix arrays. Each has n different values, right? Initially all of them are 1 because initially they will not do any change to our numbers. Okay, now for each query, if the query is larger than or equal to b, I'm gonna simply do the normal multiplication. So each number of I will be the modular multiplication of number of I and v. Okay, so that's simple, direct. Otherwise, what I'm going to do is the left value I will multiply with b, and also I'm going to find which I is greater than r and has the same mod value as l, right? So which I is greater than r and has the same mod value as l. As you can see, this will take at most b steps. So this is also fine. Obviously, you can use math to exactly find it without in O of 1 also, but this is O of b. You can use math to find this in O of 1 as well. But using math, this can be done in O of 1. Yeah, and be done in O of 1, right? So this is fine. Even O of b is fine because the time complexity does not change very much. If you do this in big O of b, this simply becomes q root n plus root n, which does not change anything to the time complexity, right? That's why I'm just doing O of b because during the contest I didn't want to think of the formula. Takes a bit of time. Actually, I was implementing this, but I could not finish implementing during the contest. My time ran out. Anyways, yeah. So this takes at most b of steps, and this mul of k of I gets multiplied with the modular inverse of the value, right? So this is how we're doing the prefix array. So it gets multiplied with this one. The start gets multiplied with the normal value, and the n gets multiplied with the modular inverse. Okay. So now we have processed all the queries. The values in the prefix array or the value in the mul array needs to be updated. So we go through each of them, and the value gets multiplied with the previous one, and the number also gets multiplied with that value. So this is just code for that. You can write in many ways. Only thing you need to ensure is this takes at most k times n steps. B times n steps, and you can verify that this takes b times n steps. Okay. This is not written very clearly, but in my pseudocode, I think I wrote it more clearly than this. For each j 0 to b, for each I 0 to n, you do this multiplication. If you read this code, you'll see that it's doing the same thing, just a little more complicated way. Then to find the final answer, we set it to 0, we find the XOR of all elements, and we return the answer. Okay. So that's all for this question. Yeah. For third question, can we solve it using stack? No, I don't think so. You will need to use DP in some form or the other. Third question was, I don't see any other way other than to do it with DP. Yeah, Dhanush, we use secretary only when there's updation. We don't have any updation over here specifically. So we can only use a prefix array. Yeah. Thank you for your kind words, Sai. Okay, now we can take any general doubts or any doubts you had regarding the previous questions. I could see a lot of people were asking doubts in the middle of the session, and while I answered the ones which didn't take much time, if you have any general doubts, usually please save it for the end of the session. Okay. Okay. General doubts, please go ahead and ask anything you want. What is your advice for giving contests? Like learn CP and DSA after giving contests, or do simultaneously? Okay, so the way I did it was do contests regularly, like at least once a week, right? Like do contests at least once a week. If you do more, it's fine. But main thing about contests is, can you upsolve it, right? So you need to upsolve it. Otherwise you won't learn much because you'll just do the questions which you could have solved, and the questions which are just at the boundary of your understanding, you will not do those, and you will just lose the value of the contest, right? So do contest at least once a week and upsolve it after the contest. So you watch the stream, or you first try to solve it yourself. Then later, if you're not able to solve it, you can watch the stream and find the answer, or you can directly watch the stream as well, as long as you implement it yourself. Okay. and upsolve it. After that, at least even if you have to see the solution, you must implement it yourself, otherwise you won't learn much from it. And then if you lack in theory, if you know that you don't know some particular theory, then you should learn that alongside. So learn theory slash practice on it, um, maybe 3-4 times a week. That's how I used to do it, or as many times. If you're very dedicated, you want to do it every day, sure, go ahead, no problem. It's not a hard limit. Roughly 3-4 times a week will be enough to be consistent. So you should be consistent, and also ensure that you at least did something every day, right? Ensure that you don't have gaps in your training, because if you have gaps, right, you're going to lose what you learned. So you don't leave gaps more than 2-3 days. It's not like you come back to CP after 2 weeks and you expect that you're going to continue learning, right? So more than 2-3 days, don't leave gaps. Okay. And if your theory, if you're sure that you know enough theory and your rating is not going up, if you are sure your theory is fine, like, if you, let's say, 1400 in your, binary search, DAP, graphs, and you're still wondering why your theory is not good enough, or you can solve outside of contest but not in contest. If your theory is good enough and you're having trouble solving during the contest, do VCs. So what are VCs? VCs are virtual contests on code forces and platforms like that. You can do virtual contests, and basically it's like it simulates a real contest and it's like a mock test. So if your theory is good enough, start doing virtual contests to increase your rating, right? So that's how you do it. I'm not able to write internship OAs properly. So yeah, that depends on the difficulty of the OAs, right? OAs usually have not that structured questions. The questions aren't that great, and they seem to be more like textbook type of questions, taken from somewhere, taken from some hacker rank, hacker lead code. So for OAs, you should basically know which company is coming. You should ask your seniors what type of questions they ask. Check online what kind of questions they ask. Practice those. There's nothing much else to do on those. Yeah. How should I practice DP? First, learn DP either from the TLE Eliminators course or from YouTube or somewhere, some competitive programmer's handbook, right? After that, do a lot of practice problems. So there are two sets which are very good. So there is the CSCS problem set DP questions, as well as AtCoder, um, DP problems, right? So yeah, there's an educational DP contest at Coder which has lies. At least the first half, or 75% of these questions are very nice and doable as well, and as well as these. So DP is about practice. Take some notes if you want. I also used to take notes earlier, and they helped me. Yeah. Okay, Manab. Your doubt on question 3, right? So yeah, question 3 was a bit tricky. So let me just go discuss your doubt on question 3. Okay. So first of all, I want you to be very, very clear what is being stored in the best array. Okay. So what is being stored in the best array? It is not some value which is decided by what we are choosing and what we are not choosing. It is simply the maximum value of DP of j minus prefix of j for all the j's ahead of it. Okay. So for all the j's ahead of it with the same prefix mod value, it's going to store the maximum value of this so that we can do updates in big O of 1. Okay. So that's why the best array is not changing. Okay. So the best array is not changing because, and you're basically asking how are we restrict, if you removed BCD, how are you restricting the removal of CDE, right? But there is nothing to restrict. Okay. So basically what the DP is doing, basically what DP is, right? Basically what DP is DP is considering all the possible values, is considering all the possible removals, all the possible removals, and taking max of them. Okay. And taking max of them, and we're using tricks to make sure that this does not take too much time. Okay. So that's what DP is. Okay. So let's say we have 5 elements. I'll show you for this case. Let's say we have 5 elements that, like you said, A, B, C, D, E. Okay. So we have 5 elements, A, B, C, D. Let me just draw the array properly. Okay. So these are the 5 elements we have, right? And you're saying If I remove BCD, what is restricting me from removing CDE, right? That's what you're asking. But let's say we have a DP value over here, right? So DP at this element, let's just call them elements 1, 2, 3, 4, 5. So DP of 4 will contain the maximum removals we can do at 4. So DP of 4 will consider this value, right? DP of 4 will contain this value. Now when we go to 5, and we already have the values of DP4, DP1, DP2, right? These values are already there. These all values are already computed, right? So when we are DP of 5, we're going to take max of DP of 4, right? So DP of 4 means nothing changes, versus this case of taking CDE, like you said. So versus best, versus prefix of 5 plus best of with the same mod, right? So best will simply be, for example, in this case, let's say best is best means taking at this position. So that means prefix of this position is getting subtracted, and sum at this DP at this position is getting, prefix of this position is getting subtracted, and DP of this position is getting added. So that's what is going to consider this case. Okay, so the DP of cases do not overlap. The DP does not need to restrict anything, because it's already taking max of DP of 4, which means the max of this, versus prefix of this, which would give you this one, right? So that's what's happening. You're in your internship season, beginner, how long practice would it take? If you're a complete beginner, it might take some time. But like, see, I don't know which college you are, or how hard your internship is, or how they exactly take the what level of coding you need. But I would say, let's say you want to become expert, right? If you want to become expert, which is good enough for most internships, I would say, right? If you want any interview or OA, mostly expert will be fine. So for that, depending on your math background, like a lot of learning CP depends on your math background. If you have logical thinking and math solving skills, like for example the maths and math contests, then it will take you very less time. But if you do not have strong logical reasoning skills, then it takes more time to build it up. So to reach expert can take you anywhere from 3 months up to a year. So realistically, I'm just telling you, I know your internship season is soon, but that's how much time it takes roughly to become good enough for anything. But obviously, if you know that you need to prepare for internships, then you can prepare the topics which they ask more. So from my experience, the most main topics which are asked are DP, graphs, and binary search. Those are the main topics they ask. And to become just good in those won't take that much time. So yeah, 3 to 4 months is a decent window, I would say. What topics are required to attempt any question? See, obviously you can't say that if you start seeing questions of 3000 rating, then not any topic is enough. Okay, but obviously you can go check the TLE course, right? The topics mentioned here, level 1, level 2, level 3, level 4 topics, these are more than enough for up to expert rating. So up to expert rating, the topics in TLE course is more than enough for that. Okay, that is for Mr. Finisher. All right, then I don't see more questions, so we'll be ending the session now. Thank you everyone for watching. Hope you learned something. If you have any doubts, do rewatch that part of the video, or do go through the code. You can sometimes seeing the code and dry running it on pen and paper helps a lot. So do check that out, right? A reminder again to check out TLE Eliminators self-paced courses, which are available if you want an ordered and structured approach to competitive programming. What about above CM? Many of these topics carry you to CM as well. But in CM, you need to know basics of maybe slightly more hard things on graph, slightly more hard things on DP. But yeah, many of these things carry you to CM. To reach master, you might want to learn more stuff like square root decomposition and stuff. You need to know. You need to know more probabilities type of stuff. You need to know. You need to practice range queries types of questions. But think about that when you already reach expert, right? You can think about that then. Anyways, thank you all and see you next time. Bye bye.